So let's talk about another way of calculating delta H. So to calculate delta H, one way we talked about was using calorimetry. Right? So if I have my coffee cup or whatever, or my bomb calorimeter, whatever calorimeter I'm using, I have to know, if it's a bomb calorimeter, how much energy will cause that calorimeter's temperature to go up by 1 degree. Or if it's a coffee cup calorimeter, I'm probably using water, and I know the heat capacity of water, which means I know how much heat it takes for the water's temperature to go up by 1 degree. So if I do a reaction in here, as we said, and the reaction is endothermic or exothermic, it will be exchanging energy with the water or with the calorimeter. And so if I know the specific heat of the water, or I know the heat capacity of the calorimeter, I can determine how much heat was required or was exchanged with the surroundings when that reaction occurred. So if I want to know, for a reaction, delta H, I recognize that the kilojoules, whatever number I get, is going to be equal to, or come from, the kilojoules that was exchanged between the reaction and the surroundings. How do I know how many kilojoules was exchanged between the reaction and the surroundings? If it's a coffee cup, I use water. If water is the surroundings, I know how much of the temperature change was for the water, and I use the specific heat to convert that as a relationship into the amount of energy in kilojoules. If the coffee cup was the bomb calorimeter, then I know the heat capacity of the bomb calorimeter. And the heat capacity of the bomb calorimeter is the relationship between how much the temperature changes in the bomb calorimeter and how much energy was exchanged with the bomb calorimeter. So I would use those relationships between the temperature change observed experimentally and the heat exchange to get the amount of heat exchanged between the reaction and the surroundings. And then I would divide that by the moles of reaction. Okay, so we talked about that. Just want to remind you guys. That's the primary experimental way of getting delta H for a reaction. But to do that, you've got to do an experiment. You've got to get a calorimeter, you've got to get the substances, you've got to mix them together, you've got to measure the temperature change, you've got to do the calculation to figure out, for that quantity of temperature change, how much energy was exchanged. You've got to know how many moles of reaction you put in. So that takes a lot of time and effort. So there's a shortcut to getting delta H's for a reaction, and that is to use delta H of formation from some tables that you would look up on the internet or in your textbook or in some other handbook. So we can use these to get delta H for some reaction we might be interested in. So we're going to talk about how to do that. So first of all, what is delta HF? What does this F mean? Delta HF is an example of a delta H for a reaction. It's basically just the potential energy change for a reaction. The F refers to, though, specifically a specific reaction between elements to form a compound. So the F here is formation. So the F means we're forming a compound from the elements that make it up. So for example, the heat of formation for CO2 is the enthalpy change, or the potential energy change, or the heat exchange with the surroundings when CO2 is formed from the elements carbon and oxygen that make it up in their normal standard conditions, which for carbon is as graphite and for oxygen is as a gas, O2 gas. So that's what heat of formation is. I form a compound starting from the elements that make it up and find out how much heat is exchanged with the surroundings, and that's delta H for that compound. Right? So forming CO2 from carbon and oxygen, is that endothermic or exothermic? It's exothermic, because I have a negative sign. Does that tell me that CO2 is relatively stable or relatively unstable? it should be relatively stable, right? Because if I look at the potential energy, if I start with these standard elements and I make CO2 and the potential energy goes down because that potential energy is given off and has less potential energy now as the potential energy goes into the surroundings, that means the CO2 compared to the elements that make it up is more stable. So looking at delta HF for a substance gives me a quantitative way of determining how stable that substance is. The more negative the value, the more stable the substance. If I have a positive value, it's probably relatively unstable, because to make it from the elements that make it up, I would have to put energy in. It would have to bring that energy in, and now it has a higher potential energy. If energy is put in to make it, that means it's unstable. It has the potential to undergo a change. So since the delta HFs represent the stability of substances, if I have some other reaction, so we just talked about that, if I have some other reaction, some generic reaction, A plus B producing C and D, if I know delta HF for A, B, C, and D, that tells me relatively how stable they are. Right? If delta HF for A and B are both negative and C and D are both positive, that means substances A and B are very stable and substances C and D are unstable. So if I do a reaction where A and B are converted into C and D, I can predict from that reaction that delta H for this reaction is going to be positive, because I'm going from a stable substance to an unstable, higher potential energy substance. I would have to put energy in to do that. So if I want to do this reaction, and if I want to get delta H for this reaction, I don't actually have to do the reaction. If I can look up delta HF for all the substances involved in the reaction, I can determine relatively how stable is it at the beginning versus how stable is it in the end. Then I know, is the energy going up? Is delta H positive for this reaction, or is the energy going down and delta H is negative? So this is the formula that I would use to do that. Yes?
How do you know that delta H of the reaction is positive if you don't have the exact number?
Well, I know the signs. So if these are both negative, that means they're relatively stable. And if these are both positive, and this is just a hypothetical, they could be any sign. If they're both positive, that means these are unstable. So I have to go from stable to unstable, I have to put potential energy in. If these signs were some other combination, like let's just say this was negative, this was positive, this was negative, this was positive, something like that, then, if I think about it, I can't necessarily predict. I need the numbers, I need the formula, because if A is negative and B is positive, well, one is stable, the other is unstable. And then if C is negative and D is positive, well, again, I have one that's stable and one that's unstable. I need to know exactly how stable or unstable they are. So I need the exact numbers for delta HF to plug in to this formula to really figure out delta H for the reaction. So generally, for a lot of substances, common substances, those numbers are known. So if you're doing a reaction with common substances, you don't need to do it experimentally to figure out what delta H for the reaction is. You just need the heats of formations for the substances involved. So, for example, here's a reaction where I want silver ions and chloride ions to come together to make silver chloride. So technically this is not a chemical reaction, but any process that occurs, if I get delta HF for each one of the substances involved, I can plug those in and figure out, if I do this process, how much energy it will either be releasing into the surroundings or absorbing from the surroundings. So to do that, I use the formula delta H for this reaction, or for this process. Since it's not a chemical change, I might put process instead of reaction. Doesn't really matter too much. So is going to be equal to the sum of all of the delta HFs for the products minus the sum of all the delta HFs for the reactants. This formula is on the formula sheet if you don't want to memorize it, or you can just rationalize it, understand why it's set up the way it is. Because if delta HF represents how stable something is, but the more negative the value for delta HF is, let's imagine delta HF for the products was very negative, and delta HF for the reactants was very positive. That would mean the products are stable and the reactants are unstable. If I set the equation up this way, I have a negative minus a positive. That's going to give me a negative number mathematically. Is that what I expect delta H for a process to be if it's going from stable to unstable? Well, okay, I asked the question backwards. Let me say that again. The reactants are here. They're unstable. The products are stable. So if I start with unstable reactants and I make stable products, would I expect delta H for the process to be negative? Yes. That's an exothermic process. So that's why it has to be products minus reactants. If I just look at the opposite situation to see what the signs would be, if I had some unstable products and stable reactants, now if I subtract and get a positive minus a negative, that gives me a positive value. So if my products are unstable, but my reactants started off as relatively stable, that means I'm going up in potential energy, and that's an endothermic process. Okay? So if I set the equation up this way, it's the only way that makes sense. It's the only way that when I actually subtract the delta H of formation values, I'll get the right sign for delta H for the process. So then I just plug in the values. So the products, I only have one product, silver chloride solid, the delta HF value, so these are listed in order respectively 1, 2, 3. So the delta HF value for that is this one. So that's a negative 127.0 kilojoules per mole of silver chloride. What units do I want delta H for the process to have in the end? Always kilojoules per mole of reaction. And the textbook leaves out reaction, which makes it very confusing. I wish they would put that in there. Because as we said, a mole of reaction isn't necessarily the same as a mole of something else. If I do this reaction a mole of times, that's a mole of reaction. That's what I'm interested in. How much heat is associated with that. But these delta HF values are not per mole of reaction. They're per mole of a substance. Because the delta HF is if I make a mole of this silver chloride substance. So what I need here to do is to multiply by the number of moles of the substance I have. So that will cancel. So that's my product. Then I'm going to subtract the sum of the reactants. The reactants I have are silver ions, which are plus 105.9 kilojoules per mole of silver ions. In this particular reaction, I happen to have 1 mole of silver ions. And the other reactant is the Cl minus, and that is a negative 167.2 kilojoules per mole of Cl minus. And in the reaction, I happen to have 1 mole of Cl minus. So in this case, since all my stoichiometric coefficients are 1, if I forgot to multiply that, it's not going to change the numbers. But I really need to focus on the units and recognize that I should do that because most reactions don't have coefficients of 1 for all the substances involved. And if I forget to multiply by the coefficients and I forget to realize that these units need to cancel, then I'll be getting the incorrect answer. So in this case, all those units cancel. Plus, we also know I can't subtract two numbers unless they have the same units. And moles of Cl minus is not the same as moles of Ag plus. So I can't add these numbers until those moles have canceled. They have to have the same units in order to add them together. So I have to cancel all the moles and just get kilojoules. So I have negative 127.0 minus 105.9 minus a negative 167.2, and that's going to give me negative 65.7 kilojoules. So that's delta H for this process. Is that delta H for any amount of this process that occurs or for a specific amount? So specifically per mole of reaction. And I don't want to leave that out because what I did was I assumed I had a mole of silver chloride, a mole of silver ions, and a mole of chloride ions. And that's true if I do a mole of the reaction. So that's the quantity of a reaction that I use to get this number. So that might seem annoying to have to do that calculation, but did it take more or less time than actually running the experiment in the lab? It took way less time, right? If I actually got the silver and chloride ions and added them together and tried to measure how much energy was exchanged with the surroundings by looking at the temperature change and using the heat capacity of the surroundings, I'd come up with that number, but it would take a lot more time and effort.